Okay. Okay, so if you look into this equation, okay, for the test normally, the test, if we provide you the question, the equation, normally it is being used, okay. If we conversely in the test, if we in the test, usually if we give you, normally it is used, okay. But in the final we just give everything, so sometimes it is not being used, so for the first question, what is the one that actually contribute to highest noise factor, means the most terrible one. So if you see this equation, okay, if you see this equation, this one, okay, so if you see this is f1, f2 minus 1, g1, f3 minus 1, g1, g2. So the one, okay, so inversely as what I told you last time, okay, if we want to the small overall noise factor, what we want to have. But if you want overall noise factor which is highest, which is undesirable lah, the worst lah. So first answer is that the first amplifier has a highest gain lah, big gain, big noise factor, and then after that this one, big noise factor for the second and the third amplifier or subsequently, and also the gain, the second and so on of the gain, it is smaller. Okay, that is the answer lah. Okay, the answer is pretty much based on the equation lah. Okay, this one figure below shows a two-stage amplifier in cascaded connection. So two. Okay, two is just because this is quiz, so I cannot give three, otherwise it's become it's long over time, okay. So this one is cascaded connection assuming room temperature of 35 degrees Celsius. IUPAC is the system. IUPAC, okay, you can search on your own. For example, if we have standard weight, kilogram, okay, it is kilogram. So that is the standard one. SI unit, kilogram for representing weight. Okay, but in some part of the country, maybe they didn't use kilogram. For example, US, they are using pound. Okay, but normally if we refer to standard, is kilogram. The same also for the temperature. Normally when we refer to it is which is it, degree Celsius or Kelvin? Okay, you can search on your own. And then, but the room temperature is this one is given 25 degrees Celsius. However, the calculation involve us to convert it to Kelvin. So 255, okay, is actually 25 plus 273 maybe, I think. You can use calculator, okay. So it is around you can get the answer like X, okay. So assuming room temperature, blah blah blah, calculate overall noise factor. So this one is actually just this equation, this one, okay. So until here, because it's just two stage, but you don't have the option of this one. So how you solve this one is actually TE equals to 4K. You try to solve using temperature. Okay, there is a temperature equation here. Is it here? This one. Okay, so you are given this temperature, you are given this temperature, you should able to solve for the F1. Okay, this one F1 is not given here. However, you can solve by using this one. Okay, this is the temperature for K lah. Okay, for Kelvin. And bandwidth is given, so 19.8 minus 80.8, so 1 megahertz, and the resistance is 75. So it is asking calculate the overall noise factor, so you just need calculate the overall noise factor. So ohm here is not being used. But let's say in the question, if we want to ask you to calculate for power, for example, that's why we have this 75 ohm. So you can calculate what? KTBR, right? n equals to KTBR. Okay, you can refer to your slide lah. Okay, KTBR. Okay, and then this one is amplitude modulations. So you are given two signal of V1 equals to 2 cos 5 times 10 to the power of 3. Okay, and this one is at cos. So okay, so this one is actually sorry, I don't like Webex, but I have no choice because I can Zoom. If I use Zoom, it will limit to 40 minutes. This one is unlimited. So we have this is 5 times 10 to the power 3. So you actually have 2 pi f equals to 5 times 10 to the power of 3. Okay, so this is your 2 pi f. And then this one is V2 equals to cos. Okay, this one is 2 pi f. So what is your f? Your f is actually 5 divided by 2 pi. Okay, times 10 to the power of 3. Okay, so this one is omega equals to 2 pi f equals to 5 pi times 10 to the power of 6. So to create for f is actually 5 over 2. Okay, pi is cancelled, so you have times 10 to the power of 6. Okay, so this one is suitable to be the carrier because it's focusing higher. This one is actually the modulating signal. So determine the full AM signal is just V AM equals to EC, which is this one is the carrier, so this is your EC. Okay, EC which is 8. Okay, plus the carrier plus the signal plus the signal which is modulating signal. So it is 2 cos 5 times 10 to the power of 3 t. Okay, and close bracket, and it's actually what cos omega ct, which is this one. Okay, 5 times 5 pi times 10 to the power of 6. Okay, this is, and then you actually expand them so that you will have the full AM signal. So calculate the transmit power. You can use whatever equation because we have been given also here. If you want to use to calculate the power, you have the option here. Here, PAM equals to P carrier equals to 1 plus M squared over 2. And you can use this equation. Okay, depends what equation you use because it's just power lah. Okay, and then this one is V, means this one is voltage. Okay, so next, the diode detector circuit. So below which part of the circuit is function as the DC blocker? So which one? So this one is actually rectifier. Okay, it will rectify to half wave lah. If we have if we have two diodes of opposite direction, it is a full wave lah. So this one definitely is half wave lah, half wave rectifier. Then this one is a low pass filter. Okay, where we actually will going to fill out the carrier frequency, and this one is the DC blocker lah. Okay, I think this one is in the module. Okay, in the module. So for those that heavy module, please try to do the exercise lah. Okay, exercise at the back. For chapter 2, there is exercise. For those that didn't have, because there is no force to buy this book. But maybe you can refer to your friend that have bought the book lah. Okay, okay, because there is exercise on AM modulations inside the book, and I think we've answered. I'm sure. Let me take a look. With answer. Okay. Try to do exercise 2, number 1, number 2, number 3, number 4, number 5, and so on lah. So if you notice now you are third year, I don't really force you to do exercise compared to when I taught you, for example, last time during digital electronics, because you can see, actually when third year we treat more you like you are more independent study. It's not the same. Second year we still okay, try to, this is tutorial, do it. The same also when first year, but third year no. The exercise you can do, but I won't force you lah. Okay. So please do your independent study lah, because if you bought the book, it's advantage for you to do the exercise and to see, to read lah. Okay. So and then you need to know what happened. For example, we have a full AM signal. Okay, this one is for full AM. Double sideband, full carrier, double sideband, full carrier. Okay. So what happened when we go to the diodes here? Means we only have the positive lah. Depends what is our diode configuration. So this is of course for diodes. If diode is this direction, for example, if the diode is this direction, what we going to have? Sorry. If the diode like here, okay, this direction. So what we will going to have? Something like that lah. But DC is actually we have current polarity at one value only, means either positive or negative. We cannot have both. If both, it is a alternate current. Okay, DC current we only have one polarity lah. So for example, either it is positive here or it can be like this. Okay. Okay, depends on the polarity. So you need to see the diode as well. So this one is low pass filter, DC blocker. Okay. So hopefully you try to understand this circuit, envelope detector circuit. Okay. Okay, so finish with that. I think the quiz is actually very easy. It's just that I'm not sure if you do the exercise, quiz is easy. Okay. Okay. So next we go through this time. Okay. There is no class on this Sunday. There is no class. We will continue the class on Monday. Okay. So last time we studied about the envelope detector. Okay. The modulation part is that where we're going to retrieve the signal that we receive, okay, from a transmitter of a full AM signal. Okay. Whether it is full AM signal or single sideband signal, vertical sideband signal, depends. And single sideband we can even further divide to single sideband suppressed carrier or single sideband full carrier, depend which one. Okay. So this is envelope detector known as rectifier detector and diode detector. This one is for the full AM lah, double sideband, full carrier. Okay. So this is the things that we have, where the thing that we receive, which is full AM signal. So this is the general equation. Okay, the general equation or the full AM signal. So this is our low pass filter, and this is our DC blocker. So this is the advantage of having envelope detector. So you should be able to know. So this one is what is the time constant. Okay, discharge rate, the discharge rate here. Okay, so tau equals to RC. So if we have RC that is too large, it will look like a ripple. Okay, sorry, if it's too large, it will look like a clipping. Okay, like a clipping like here. Okay, but initially we want it to have a smooth shape lah. Okay, as smooth as like this one. Okay, for example lah. Okay, not smooth like this one, the shape envelope. Okay, so if your RC is too large, you're going to have clipping. If it's too small, you're going to have ripple. So this is the envelope detector. This is the impact of we have RC value. Okay, so if it's optimum, it's like this. Where we have the shape almost like smooth and like this. If it's RC is too small, we're going to have like a ripple. Okay, when you wait. Okay, so if we have the value, whether it is too high or too low, for example, if RC value is too small, you're going to have effective like a ripple. you see, can see, right? And I mean, if too small, if too large, it will look like a clipping that is being cleaned. If it's too small, it will look like a ripple. If too large, it will look like clipping. Okay. So this one is the optimum value lah of our RC, time constant. Okay, next, this one is actually the full AM, still full AM. So this is our envelope equation, this part, and this one is our carrier, and this one is our what we call as a diode switching function. Okay, so here the diode switching function is given equals to 1/2 plus 2/pi cos omega ct plus 1/3 cos omega 3 omega ct and so on. You see here, this one is cos omega ct, this one is cos 3 omega ct. So the next one, you can guess what, right? That what is the next one? If you can you guess what is the next one? If this is cos omega c, this one is minus cos omega 3 omega c. So what is the next one? Yes. The next one will be 1/5 cos 3 omega ct plus. And the next one will be minus 1/7 cos 7 omega ct. So so it is actually using the, if you remember your signal and system, so this is have using odd numbers, n equals to 3, n equals to 1 3 5 7. So diode switching function, it should be given. If it's not given, just is as a KT lah. Okay, if it's not given, it is KT. If it's given, they will give. You don't need to find what is diode switching function. Okay, so if it's not given, just assume it is KT. And if it's given, they will give you what the function. You don't need to predict what is diode switching function. Okay, so we have VD is actually V point B. Okay, here VD is actually VD is V diode. VD is V diode, where V actually point B here. So you're going to have from AC to DC. Okay, from alternate current to only to direct current, one polarity lah. So you have EC plus VM cos omega ct, and this is your diode switching function. So in the end, you will have 1/pi EC plus VMT. This is when they give you the diode switching function. When they give you diode switching function, you can know it's actually 1/pi. You can take it up 1/pi lah. So this one, then you have higher frequency terms. Higher frequency term, for example, 3 omega C, 5 omega C, 7 omega C, that is higher frequency lah. Okay, the repetition, harmonics lah. Okay, so then we put to lowest, go to the low pass filter. So we only allow low frequency to pass through and higher frequency to be filtered. So that's why it filter up everything. Okay, everything of the higher frequency, which is omega ct, and also diode switching function. Given that diode switching function have a frequency that is higher lah. Okay, you see here diode switching function. Okay, so we remove everything. We only have, okay, when it pass through the filter, we only have 1/pi EC plus VMT. Okay, if KT is if this one. Okay, and V point D is at V at the output here. Okay, when we have here, when before it go to D, it goes to DC blocker. You see here, have 1/pi EC plus VMT. So in here, the DC blocker is this one. Means just like a line, just like a line. Okay, so this one is a bit boring. So please do exercise on the past test and past final. I think I already shared to you lah. Past test and past final. If you want more, you can request for me. I will share it, but maybe we can try to solve together to see the working step lah. Okay, because I don't have the schematic answer, but what we can aim together is actually for for the working step. When your working step is correct, inshallah your answer will be correct lah. Or if your answer is still not correct, at least you get the more majority mark, which is coming from the working step, not the final answer. Okay. So here is V after diodes, and this V.C after low pass filter, and the next one D is the voltage after the DC blocker. So C is here, means it is before the DC blocker, so you have 1 over pi C plus VMT. This one definitely not is not direct current lah. This one we having shape lah. This one is obviously is a number lah, because this one is EC, just a number. For example, 5, so it will be 5 over pi. So that's why this one is DC blocker. When this one is DC component, they're going to be removed when it go to the DC blocker. So we no longer have EC here. We only have 1 over pi time VMT. Okay. So since capacitor C prevent direct current, EC over pi going through it. So you should know lah. Okay. If this one is diode situation, it is not for you to predict. Okay, either they give it, or you just, for example, you can just assume it's KT lah. Okay. So this is the pretty much what I already have in your quiz. Okay, but it didn't ask directly because quiz is supposed to be simple, right? I intend to ask you actually from here, what is the shape that you have? Here is what is the shape you have, and so on. But I must be fair, because the quiz is only 30 minutes and need to cover chapter 1, chapter 2. So it cannot be too much lah. But you yourself need to know. For example, here, you see? Okay, you should know how to get it lah. Okay. So the next is this demodulation. Demodulation, where we have, first is that we have the using diode rectifier. Now we're using square law detector. When we say square law detector, means it involves something that is going to be square. Okay. Okay. So you have here is the AM double sideband full carrier. Okay, AM double sideband full carrier. Then it will go to square detector. You see here, Y equals to X square. So the output will be the output is to be XT. Okay, the output is to be XT. For example, you see here, XT is what? XT is equals to whatever that you have here going to enter and going to be square. So that's why this one is double sideband full carrier, and you just put square because it's undergo square law detector. So everything just actually simply be square. Okay. Okay. Where is Hisham? Not Hisham already. Not Hisham Muhammad already. Another Hisham. Never mind. Maybe they don't realize today we have class, but it's okay. I already recorded. Okay. But I hope to Zenhui, please check if I share today recording and also previous one. Okay. Okay. So here you see this one is square law detector. So you just square. Okay. And this square, you just refer to the appendix. Okay, the appendix page. Or if the appendix didn't give you the question, you should be able to know lah. So I think this is not that difficult. This is just actually you do the square. Yes, there is in the appendix. You can try lah. Okay, so this one is actually A, C. Okay, let me do those things. Okay, so you have AC plus MT cos omega CT. So what you actually know do is AC. Okay, you expand it first inside. So AC cos omega CT. Okay, then plus MT directly. Okay, plus MT. MT is actually your signal modulating signal. Okay, but we just put MT first. MT means modulating message signal. Okay, so that is M lah. So we have MT cos omega CT. Okay, then we close the bracket. Then we don't forget to put square because it's a square law detector. Okay, then you just explain normally what you learn in your mathematics, admits. Okay, so it's actually nothing special about it. That's why you have to SE, and you have this one as the square, and this one is as the square. Okay, and then it goes through this one, what we call as the DC component, because we have the capacitor. Okay, so when it goes through the capacitor, it remove the DC signal. So you see here, we this one is from the output. Okay, from the output, the square law detector. So you have a DC component. This one is totally DC, because this one is just a number. Okay, AC is actually amplitude. Then you have ACMT. So this is the message signal, which is your information signal, the one that you trying to send. Now you get it back. Okay, but maybe small in magnitude or whatever lah, depends. Okay, depends. But at least that is your signal having the same pattern or almost similar information lah. Okay. Okay. So then then you have this is ACMT. Okay, as your message. Then the rest is harmonics. Okay. How you know it is harmonic? For example, this one is m square. For sure, if it's for example 300 hertz for the information signals here, for example 300 hertz, so here will be 300 square. So you're going to have more like square. So the same with this, all of them is actually the harmonic frequency. Why is harmonic frequency? You see here. Okay, so they are all harmonic frequency even here, because message signal which is the modulating signal is still actually have a harmonics lah. Okay, this one is totally DC component, just number. This one is our message signal, the fundamental. Okay, the information signal with the fundamental frequency. The rest are having frequency which is integer or multiple. For example, this square, this one will be double frequency, because 2 omega c, which is 2 times 2 pi f. So f is actually equals to 2f for this alone. But don't forget, we have this one, and we have this one, which also having cos or sine inside. Okay, so it's double, triple, and so on. So this, of course, so that's why this one is harmonics. After going through low pass filter and see, so output is desired message signal because this is square and this is getting rid of DC components. So you're getting rid of this DC component. Okay, then you have this one and this one. Okay, after it here. Okay, after the DC blocker, then it goes to the low pass filter. Okay, so low pass filter, definitely it remove all the higher frequency. That's why this one is removed, this one is removed, this one is removed, this one is removed lah. And of course this one is removed because this is omega c. So all of them removed. This one is also removed. You only left with this. Okay, low pass filter, which is in this case the modulating signal is the low frequency lah. So it only pass through this lah. So in the end you get the message signal. The rest are being reduced by DC blocker for the DC component, and the other is being reduced or being removed by the low pass filter. Okay, so this is using, if you want to demodulate double sideband full carrier using square law detector. Okay, the next is the double sideband suppressed carrier. Okay, so we're going to suppress our this one. We already suppressed the carrier, but how we're going to demodulate them, how we're going to receive our signal back. Okay, sekejap. Okay, so since envelope of the modulated signal is different from the modulating or message signal, remember just now is the demodulation for full AM. Okay, so now is the double sideband for suppressed carrier. So we cannot use use the previous circuit, either diode detector circuit or square law detector circuit. We cannot use them because this one is for because the one is for full carrier, means we have double sideband, we also have carrier. Here the carrier is being suppressed, so we only have double sideband. Okay, so since envelope of the modulated signal is different from the modulating or message signal empty, one cannot use the envelope detector to demodulate AM double sideband space carrier. So that's why you cannot use because it's different. Okay, its demodulation can be performed using asynchronous detector. Okay, synchronous is it is being synced lah. I think this word is, you pretty much know what does it mean. Synchronous mean is a sync, always change accordingly lah. Okay, so also known as the coherent detector. So it's coherent. I think coherent is I think you can search internet what is the coherent. That time during secondary school you learn what is coherent. Okay, so there is two names for the detector in double sideband separate circuit. Is either synchronous or is also other name of it is a coherent detector. Okay, so this is a synchronous detector. Okay, a synchronous detector for double sideband suppressed carrier. Okay, double sideband suppressed carrier. Okay, so the signal is being come to the mixer. Okay, we call this mixer, or you can call it local. You can call it depends. Okay, it's here. Here this one is obviously a mixer. So you need to able to appreciate if you are given this or you are given this, which of them. Okay, because this one is definitely is mixer. This one is a additional. Okay, you add them, combine them. Okay, so you have double sideband suppressed carrier, then you have mixed them with a local oscillator. Please know that when you use synchronous detector means you should already have the information of what is the carrier frequency. For example, if you are using 10 gigahertz, for example, 10 gigahertz, the local oscillator, we also should know what value of the frequency that we're going to fit to our local oscillator. It must be the same. So that one, when you use the system, you must be able to know what is the predicted carrier frequency is going to be used. Because when you want to demodulate them, you need to know the frequency of the carrier. Okay? If not, you cannot demodulate correctly lah. So that's why here you need to have the information of what signal is being transmitted using what carrier. Then local oscillator CT, so cos omega CT. So this is being tuned to the frequency of the carrier, not the modulator and the carrier. Okay. Then multiply. Okay. So this of course is a multiplier because it's going to be multiplied. So when it's multiplied, that's when you have a square or whatever, right? Okay. Then you have the output, which is the XT. Then XT, you go to low pass filter. So you remove all of the higher frequency, only leaving the low frequency, then it's going to be pass through. Okay, so this is double sideband suppressed carrier demodulation. Okay, so for this one is we multiply. Okay, then you get some answer. Okay, we go to the later on. Okay, it's here. Okay, I thought I want to do it for you, the writing, but it's already here. Okay, so a local oscillator to generate a local carrier is required. Yes, like I told you. Okay, the generated signal has to be synchronous with the carrier signal that is used as the transmitter. So this is what I told you. Okay, already told just now. Okay, so this is the mathematical thesis. So this XT is XT for here. Okay. Then you have AM double sideband suppressed carrier in time domain. Okay, don't forget the T. Then mixer with the cos omega CT. Okay, cos omega CT. Then you expand it. You know that amplitude modulation double sideband suppressed carrier. You don't have carrier. You only have the message signal or modulating signal. That's why you only have empty here. Okay, this is modulating signal. This one is carrier signal. This one is the one that being introduced by the local oscillator, cos omega CT. Okay, then you notice that this one is actually the similar frequency. So it is cos omega, cos square omega CT. So if in the event that it need to be solved for this one, for example, this one is already inside your appendix. Okay, depends on what the question wants you to do lah. Okay, so you see here output from the mixer, yes, correct, just now like I told you. Then you can do the trigonometry identity to get, for example, this is cos omega cos square u. Then you do the you refer to the appendix, or you have your own trigonometry skill already, so you know it's half 1 plus cos 2u. Okay, so xt, then you increase further. Okay, for example, you have empty you can take it out. Okay, empty you can take it out, then you have 1 plus cos omega ct. Okay, this one. Okay, and this one is xt, this one. Okay, this one you have this. Okay, so you know, this one is xt, empty cos square. This one is cos being expanded. That's why you have this lah. You have this, and then whatever you have this, you put it inside here again. Okay, with m as well lah. So that's why you have this m half empty in bracket 1 plus cos 2 omega ct. And after that, we expand them. So we have half empty plus half empty cos omega ct. So when we go to the, after that, it need to go to low pass filter. When it go to low pass filter, obviously this one will be removed. Why? First reason is we have is already a carrier frequency, mean frequency is far higher than the low pass filter. And the next one, it is actually having 2. So it's actually what? It's actually like the harmonics lah. So of course this one is a higher frequency lah. That's why we remove all of them. So you only left with this. Okay, so you see, you should know I think you know what is low pass filter function, but sometimes you can forget lah. Okay, means it's on when going to the low pass filter, we only get the original signal, but original signal may be not similar in amplitude, but at least similar or most or approximately similar in terms of the shape. Okay, so this one, no worry. This one is, yes, it is half, but it's just a value that we can compensate again. For example, if you want to for it to exactly to be to have message signal, and we don't want this one small one, maybe we can go to the gain of 2, for example. So half 2 empty times 2, you will get empty again. Okay, which is the same original signal. Okay, but for here, it's already okay. It's actually already satisfactory. We already have the information signal, but it's just it being reduced. Not sometimes reduced because of the noise present. Okay. So this one is impact of the carrier frequency phase error. Okay. So this one is the same thing for the double sideband suppressed carrier. But let's say if we have the phase error. Okay. What we mean by phase errors? Okay, when there is a phase or frequency difference between the locally generated carrier frequency, this one is locally generated, which is this. Okay, and input signal double sideband suppressed carrier. So we're going to have this phase error if we have a difference between this one and this one, because initially they should be similar. Okay, not similar in terms of amplitude, but similar in terms of the frequency and angle lah, the one that we want to send. So here, okay, if we have phase and frequency different, is we have here. Okay, we have frequency difference, which is delta omega, and this one we have the phase different. So this one is actually phase, right? This one is actually frequency, but together they are what? Together they are angle. Okay, together they are angle, like just like cos theta. So it's together they are angle. So this lead to distortion during the modulation process of double sideband suppressed carrier. This is distortion. So you can actually, you don't need to remember this. You need to understand actually. Okay, when we have error, the error can be contributed by our frequency different or our phase difference. Okay. So this is the mathematical analysis. So this one also straightforward. I think no problem in you understand this. But if you have problem, let me know. So you have this, the mixer output. The mixer output. This is your mixer. What is coming out from the XT in case there is a phase error or there is frequency different. Which one? Okay. Next, you have so you from the mixer you have empty cos omega ct plus phase. You see here you already start to have what? You already start to have phase different. Okay, phase different. This one is your signal, the double sideband suppressed carrier. Okay, this one is double sideband suppressed carrier lah. Okay, then trigonometry. Why we say double sideband suppressed carrier? Because you don't have carrier component. Okay, if full AM in the envelope equation, we have the what we call it? We have the carrier component, okay, but we don't have here because it's double sideband suppressed carrier. So you use this trigonometry identity. Okay, you have here cos A, cos B. So cos A, for example, you can put here cos A, you can put here is cos B. Depends what you want to put. Okay. So, but it should be cos A, cos B, then you have half cos A minus B plus cos A plus B. Okay, at least you show this, for example, you can put this one is cos A, this one is a cos B. For example. Don't burden yourself. Something if you can calculate later, for example, this one, right? Cos A, cos B. So you can actually just you do the simple mathematics, cos A, cos B, you get 1, and so on. Okay, using this equation, cos A, cos B, and you have this. Okay, then using this trigonometry, you will obtain this one. Okay, you can try this at home by multiplying both of them together. What you're going to have it? You're actually going to have similar things. Okay, by letting X into the low pass filter, the message signal can be recovered. Okay, by letting the XT signal into the low pass filter, the message signal can be recovered. So you see here, XT into the low pass filter again. So when it goes to low pass filter, the higher frequency is being removed. You see here, where is the higher frequency? Is it A or B? Which component have higher frequency? Can you tell me in the web section? Which have the higher frequency? A or B?
B betul.
So it's B because it's a double. Okay, first is double, for sure it's higher. Second is actually omega C, so it's always higher. Okay, the one that is low frequency is actually the message signal. So that's why this one is totally removed, all of them, and you only up having A. Okay, this one no problem. This one we can remove it or we can touch it, we can amplify it too. Then in up we can have this one. Okay. So you can do the exercise. I admit it's a bit boring. Okay, until you actually do the exercise and you know what you don't know. Okay, now you don't know what you don't know. Now you just listen. So it's quite boring lah. So you see implication due to carrier phase error. Okay, today this we will stop here, but I will finish first this one. So the error cause distortion, therefore the tuning of local frequency signal must be fixed. Okay, so when we have this error, which is the carrier phase. Okay, just now we have frequency different or phase error. Okay, so okay, see first the next slide. Okay, okay, never mind. Okay, so the low pass filter output has the factor of cos phase. Okay, have the cos phase. Just now, if you go to the previous slide, you have the phase error here. Okay, So you still have the phase error here. Still is being carried is I mean dia dibawa sekali. The error is being propagate to the next stage. So we need to fix it. Okay. The error cause distortion. Therefore, the tuning of local frequency has to be fixed. Okay. So the low pass filter output has the factor of cos this one, which is the angle of the phase. We have the phase error here. So you have yt equals to 1 over t mt cos phi. Okay, so if you phase error is 0, okay, if your phase 0 is 0, means there is no error. So you're going to have exactly as your message signal, modulating signal. Whatever here, this one is okay. This one is the thing just constant lah, but at least you have totality of your signal, the modulating signal, the information signal. The next, if you have phase error is equals to pi over 2, which is 90. Because this is a cos, okay, this is a cos. So this is 0. This is your 90. So this, if we have phi equals to pi over 2, so this will be 0. Anything times 0, you're going to have 0. This one here. Okay. So Costa loop or phase lock loop is used. Okay, we're going to use phase lock loop. This one is actually stands for phase lock loop. Loop, I think, maybe, I don't know whether you learn or not, means it's going to be like a loop. Loop, for example, and lock. Lock mean all of the root is being locked lah. We don't have something that is open lah. Okay, so Costa loop or phase loop is used. Phase, phase lock loop. Now we're going to fix on the phase. Okay, that's why this is phase lock loop. So phase lock loop to ensure that the LO local oscillator, okay, is fixed. Okay, we're going to fix the error. Okay, with reference to the carrier signal, which result in a maximum message signal. Okay, so that's why we use phase loop lah. Okay, to fix the phase error. Okay, then in the end we can get a maximum message signal lah. The loop has a voltage controller oscillator VCO. Maybe you already read somewhere. Okay, VCO. What is VCO? They will be locked. Okay, so to the carrier frequency of double sideband suppressed carrier with only small phase error. So maybe this one I will detail in the next session of the class. Okay. Wait. Maybe in the module you read first. I will go through it later. Okay, you read on the module on the page 57. Okay, I mean you can continue reading lah until the end, because it's going to be enough. Okay, I'm going to finish until 65. Okay, then we will focus on doing exercise together, or we can try to do the exercise in the modular exercise too. Okay, I don't know if Zenhoi want to share the exercise too to your friend. Okay, those that don't have the module, actually I a bit sebesalah lah. I feel a bit 50-50, because if maybe the author of the book will not permit, but the students still need to do exercise. So how should I do? Okay, so because the module have exercise 1, 2, 3, 4, 5. Okay, so you can do 1, 2, 3, 4, 5 if you want. You can do 1, 2, 3, 4, 5. Okay, and maybe in the next class, which is on the next class on the 28th. Next class on 28th. Okay, on the 28th November. Maybe I will discuss on the maybe I will discuss on 1, 2, and 3 lah. Okay, for 5 you can try on your own, but because I don't think we have time to cover for 5 lah. But for you, for your test, please you can try to do exercise number 1, number 2. I think number 1, number 2, right? Because number 1, number 2, number 3. Okay. So you can try to do the on the full AM lah. Okay, on the full AM, because actually you need to do at least full AM, because full AM is the basic. When you understand full AM, you can answer question on single sideband or vertical sideband. Okay, but the problem the thing that you need to try first, exercise 2, number 1 and number 2. Number 3, 4, 5 you can do on your own lah, but of course if it is encouraged to do all of them lah. Okay, so that we finish the class, so we will see on the 28th. Okay, we're going to discuss question number 1 to 3. Okay, thank you.
Thank you, Doctor.
Okay.
Thank you, doctor.
Thank you.